So I want to recall a definition or a theorem with you before we go on. Uh, it has to do with a base of a topology. Now, it's very likely that with all that's gone on, you've forgotten what a base of a topology is. And if that's you, I would like to ask that you kindly pause the video, pull out your book, go back, review quickly what a base for a topology is, and then come on back. So hopefully you did that. So a base for a topology, it's a set of subsets. It's a collection of subsets of X, where when you union everything in your set R, you get X. And in fact, every open set can be written as a union of things in your set R. That's the key, is that a set R, I'm going to write up here, R is a base. Whoops, that's not very nice looking. R is a base for a topology, F, if every open set in F can be written as a union of things in R. And so one of the deep questions is, how do you know when a random collection actually is a base for a topology or not? Because there's lots of topologies. And so we have this theorem that we actually proved. We spent a lot of time in this, and not for no reason. So here's the theorem. If you have a non-empty set X, and you have R is just, I wrote it as a subset of the power set of X. It's just a collection of subsets of X, okay? So the question is, when is this set R a base for a topology F on X? Well, it's a base for a topology if and only of one. You can write X as a union over everything in R. When you union up every set in R, you get all of X. And two, this was the tricky one, if you have two sets in R, and I can find something in their intersections, a little point, this is a point in their intersection, then there's another set in R where actually X lives in the intersection, it lives in that W, and the W is contained in the intersection. And so we're going to need this theorem to prove the following theorem. So let's go ahead and look at the statement, and then we're going to prove it. I don't know how long this video will take. I apologize if it goes real long, but this is a proofs course, and these are some pretty important ideas. So here it is. This is kind of the heart of why we care about metric spaces and, metrics at all. And the reason is that if you have a metric on a non-empty set X, anytime you've got a metric, any metric, and you take the collection of all the open balls that we just looked at, take all of them. So my set R is the set of all open balls. Then that collection is a base for a topology on X. Okay, so the big takeaway, even if you don't follow the proof, the takeaway here is that when you have a metric, there is an inherent associated topology. And so I'm going to go ahead and work through this proof with you as best I can. I want to try to be timely, but I also would like you to see how this goes. So please realize we need to verify, to prove this, we need to use theorem 2.3.8. We're going to use this, and we just have to verify that the collection of these open balls satisfies 1 and 2. We need some notation. So let's say, look, let's let R be the set of all open balls in X. Okay? Now, we need to realize right away that we're using theorem 2.3.8, and so we should say that. So it suffices to show the two conditions of theorem, 2.3.8. That's what we have to show that R is a base. You know what, I really should have, I don't actually like this proof. I should have said we need to show that R is a base for a topology. So let's say to show R is the base of a topology, and then we'll make that a lowercase. It suffices to show that the two conditions of theorem 2.3.8 will say are satisfied. Okay, So first off, we have to show that I can write my entire set X as a union of these open balls. And so here's what we're going to do. We're going to point out that since for every point X in our set X, X belongs to the open ball of radius, I'll just say 1. Please realize I could change the radius to whatever I want. X is always in the open ball of radius 1. And that, by the way, this open ball is in R. Okay? And so it follows that if I've got every single thing in X is in one of these open balls. And so if I take the union of all open balls, when I'm unioning, I'm going to have doubles, right? I might pick up X lots of different ways, but when I write the union down, I just get X one time. So it follows that the union over all open balls B in our collection R, this union does indeed give X. So we've shown that 1 holds. Well, that was nice. It wasn't too bad to show 1. So now we have to show that 2 holds. All right. So next, we're going to go ahead and we're going to choose 2 things in my set R. Let's go back up and look at 2. It says you have 2 of these things, and you pick something from their intersection. So our R is a collection of open balls. So I need to choose, whoops, I said that already. Let's choose 2 open balls. Let's go ahead and label them. Let's say the open ball of radius epsilon centered at a point X, and the open ball of radius delta centered at Y. And let's point out, please, that epsilon is bigger than 0, delta is bigger than 0, and of course, X and Y, these are just points in my set X. That all is relatively clear, but somehow we can make it crystal clear. Okay, so now I'm going to go ahead and I'm going to assume that Z is in here. It's in the intersection of these 2 open balls, because that's the situation that the theorem talks about. If they don't intersect, if none of them ever intersect, then we're done trivially. So I can go ahead and assume that a Z lives in that intersection. And here's where drawing pictures to the side, I'm going to let you into my mind just a little bit here. Drawing pictures to the side is really helpful. So here's this point X, and here's this point Y. And let's suppose that I've got this radius epsilon, looks like this. Maybe it's quite large. And let's suppose that my radius delta, let's pick pink, around Y looks like that. Maybe it's smaller. So here, this is delta. I think I did X was blue. This is epsilon. And so where are we picking Z? Z lives right smack in the center. And somehow, just from the picture, you can see that this is going to be true. We can definitely take a little ball of that radius, a little tiny radius right there, and squeeze it in between those 2 where it's contained in both. It's contained in the intersection. Somehow we actually have to write that down. So let's do it. And let's first off realize that, hey, if Z is in here, we can say the distance between Z and X, you know it's less than epsilon because it's in that open ball. And you also know the distance between Z and Y is less than delta because Z is in that open ball. And so how do we actually come up with this little ball? Well, I'm going to switch back to black. So I'm going to go ahead and I'm going to let gamma be the minimum of epsilon minus the distance between Z and X, and delta minus the distance between Z and Y. Now, it may seem like that I just pulled that out of thin air, but actually, look what I'm doing. I'm interested in, let's draw it like this. I'm interested in this little distance right here and that little distance right there. So I'm saying, look, take the distance between my point Z and X, okay, and subtract whatever radius epsilon is, and that's going to leave me this little piece left over right there. And then take the distance between Y and Z, this distance, okay, delta minus that distance is going to leave me that little piece right there. And then I don't know which one is bigger, so take the smaller one, and that's going to be the right radius. Let's also note that, I'll switch back to black. Let's point out that gamma is positive. That's an important detail, right? If this is going to be a radius of an open ball, it has to be positive. I'm going to make the claim that, let's erase this here. I'm going to make the claim that the ball of radius gamma around z is contained in the ball of radius epsilon around x intersect the ball of radius delta around y. And if I want to show that I'm in the intersection, then I just need to show that I live in this open ball, and that also each point in this ball lives in both of these open balls, this one and this one. So to do that, I'm going to choose some point, let's say W, in my ball of radius gamma around z. And what do we need to do? We need to show that I'm in the intersection. So I'm going to go ahead and point out to you that by the triangle inequality, the distance between W and X is less than or equal to the distance between W and Z plus the distance between Z and X. That is the assumption of a metric. I'm guaranteed that I have this property. Well, gosh, the distance between W and Z, that's exactly, at most, gamma. So this is less than gamma plus, and the distance between Z and X, well, I'll just write that down again. How do we define gamma? Well, I don't know exactly what gamma is. It's a minimum, but I know that it's less than or equal to this distance. So this is, gamma is less than or equal to epsilon minus the distance, oops, that's distance, not delta, minus the distance between Z and X plus the distance between Z and X, and that's just epsilon. And so I've just shown you that when you pick something in here, call it W, the distance between X and W is less than epsilon, which means that whatever's in here is in there. And then I can do a similar argument. I'm not going to write it out just for time's sake. So a similar argument shows that W is also in the ball of radius delta around y. So thus, this ball of radius gamma around z is indeed contained in the ball of radius epsilon around x intersect the ball of radius delta around y. So part 2 from the theorem holds, and we can say thus R generates a topology on X. And so any metric, the collection of the open balls generates a topology on X. So let's stop this video here.